In this video, we will be continuing our discussion of projective geometry, something I discussed in a past video. If you haven't watched my first video on it, now would be a great time to do so, because I will be building off of concepts shown in that video. And I'm linking it in the description for further reference. Either way, let's get started. Suppose you have a quadrilateral ABCD shown here, and the point E is the intersection of lines AD and BC, F is the intersection of lines AB and CD, and G is the intersection of lines AC and BD. And we let EG intersect the line CD at point F prime. Then the key claim here is that the points F, F prime, D, and C form a harmonic bundle. In other words, this cross ratio here is equal to -1. So how do we prove that this cross ratio is equal to -1? Well, we have that F prime is the intersection of EG and something else, and D is the intersection of EA and this line, and C is the intersection of EB and this line. And the point F is the intersection of EF and this line. So therefore, if we project it through E, this is equal to if this point here, let's call this E prime, then this equals F E prime A and B. And now what else can we project this through? Well, we also have this point G here. So we could try projecting through G. And when we do that, after projecting through G, we end up getting the point F stays where it is because we're projecting from this line here to this line here. And then the point E prime goes to point F prime. So we still have the same thing here. But now the catch is that the point A gets mapped to point C, and the point B gets mapped to point D. Because AG intersects at point C, BG intersects at point D. So therefore, these two cross ratios are equal. And as I discussed in my past video, if two cross ratios are still equal even after swapping the 2 points, that means that it's equal to -1. And we have shown this lemma here. Now we have the following configuration shown on screen. We have a triangle ABC and points D and E on side BC such that angle DAE is equal to 90 degrees. And the key lemma that we're going to present here is that the cross ratio ED with BC is equal to -1 if and only if AD bisects angle BAC. So how do we prove this? Well, there is a nice trigonometric proof, but we're going to present a synthetic solution, one that only involves similar triangles. So let's go ahead and construct a line perpendicular to AD passing through D, so that is parallel to AE. Let it intersect at points P and Q. Then by the parallel lines, we have that triangle PBD is similar to triangle ABE. And using the similar triangles, we get that PD over BD is equal to AE over BE. And this implies that PD is equal to AE times BD over BE. And now we can use the same logic on similar triangles CQD and CAE. We have that QD over CD is equal to AE over CE. And therefore, that means that QD is equal to AE over CE times CD. Now we will investigate when these two quantities are equal, PD and QD. On one hand, we can use the length conditions and get that this is equivalent to AE times CD over CE is equal to AE times BD over BE. The AE's cancel out from both sides, and we are left with this. When we cross multiply, we end up getting BE times CD is equal to BD times CE. And from what we discussed in the past video, this is equivalent to ED and BC, making a cross ratio of -1. Now let's examine the other side. If PD is equal to DQ, then because this angle here is 90 degrees, and we have this common length AD, by SAS congruence, we can say that triangle PDA is congruent to triangle QDA. And therefore, angle PAD is equal to angle DAQ. And this means that AD bisects angle ABC. Therefore, these two conditions are both equivalent to PD is equal to DQ, and we have shown this lemma here. There's one last fact that we're going to present in this video. And that is, if you have points A, B, C, and D on the circle here, and you have a point P here, let's go ahead and draw in the lines AP, BP, CP, and DP. Let's say they hit again at A prime, B prime, C prime, and D prime. Then we have that the cross ratio ABCD with respect to the circle is equal to A prime, B prime, C prime, and D prime. The proof of this fact is a bit too computational for this video, but the main highlight is that we can project through points P not on the circle as long as we project onto the same circle and use the second intersection. And in the case that AP is tangent, we just use A again. So the three main lemmas that we discussed in this video are 1. Any quadrilateral, whenever you draw in all the intersection of the diagonals and the sides, they can end up inducing a harmonic bundle. The second is that right angles and angle bisectors can also induce a harmonic bundle. And the third one, as I described just right now, is that we can project through points P that are not on the circle as long as we project onto the same circle. And we will be needing these facts in my next video on 2023 USA GMO problem number 6. So thank you so much for watching this video. See you in the next one. Please subscribe if you'd like to see more videos.